velocity situation, or if we are in a general situation, like in the exit case, or in the solution situation, or in the switch situation, we are able to control the action. Okay, so I will say for result like this. So let me just finish the argument here. We have here over lambda square, which is a constant, right? And this is the same as lambda t, because t is lambda square lambda t. So lambda t is constant. So if n naught is negative, lambda is a positive parameter, so it will go to 0 in function time, so this is the graph. And if you integrate back to the graph, we get lambda t is n naught t minus t. And since lambda is 1 over the exponent number 0, we get the growth rate. Let's put this here. If we have lambda naught is 0, it becomes the same as the blue. This is a solution situation, so let's say 0. And if lambda naught is positive, the lambda increases, and this means the opposite. So the lambda is the solution is flattening. But this flattening goes jointly with the fact that epsilon becomes bigger. The fact that t becomes bigger as well, the epsilon becomes bigger, and we go away from the solid. And this is the exit. And once we exit, we have no more argument, but we have to stop the analysis because we don't know what to do after. So, and this is in contrast to the situation that we deal with Lacanissian flag or Triga Lacanissian flag that were able to do classification around solution for the nominal Gaussian equation, for example, for nominal wave equation, and they were also to control, they were able to control outside the solution by putting no return lemma. So we do not have such no return lemma for the Kennedy equation so far. So once the solution exits, the neighborhood, we don't know what happens really. Okay? We just know that it's very flat, it's close to the minimal solution, but we don't know. Okay, so from this we see the three cases. Now if I take the full solution, we have the epsilon part of the control. And this is controlled using a Lyapunov functional that I cannot find here, but I will call it f of t. And the Lyapunov functional is, let's say, it will be controlled above and below by h1 norm of epsilon times a weight function. The weight is exponential for y negative. For negative y, so it's a localized norm. I'm not able to control the epsilon everywhere. And for positive y, it's like y squared. And this is why we need a weight on the initial data. And we need 1 to the 10, but here I put 1 to the 2, where we need some more. And this is why we have to do at some point, so we put 1 to the 10. So it's a kind of a strange quantity that looks like the energy at the level of epsilon, plus some Dirac density at the level of epsilon, so it's a mixed quantity that will control at the end, that will be decreasing, so we're going to prove that f prime plus a positive quantity, so let's say a local quantity, something like this, dy, which is negative, but in fact will be controlled by t to the 4. And what we have t to the 4 is because in the equation we have t to the 2, the square. So put this energy vertical equation of epsilon by epsilon itself, and we lose cosine part. The epsilon part is absorbed in this term, and then we get, by cosine we get the d square, so we get the d4. So if we improve the answer, we improve this part. And to prove this, we do need that y has a good decay on the right, the good decay for y positive. But at least we get a nice way to control the epsilon. So I cannot say more right now, but we do have a nice control of the infinite dimension part of the solution, besides a complete knowledge, I would say, of the finite dimension analysis, which is the difference. So in reality, of course, when you reach everything, you have something like this. So 0 over lambda square is not really constant, of course. We get something like this. So the variation of 0 lambda square is in 2 times. It's controlled by something like this coming from the equation. Plus, let's call this x of t. So it's a square of the norm of epsilon. Or lambda square of t1, for example. And there's some other control to that. So what you see that 0 lambda square is not really constant, but it depends only on what happens at the time t1. Okay? And of something which is of high order, because it is small. So 0 lambda square is a more constant. See what happens. Okay, so I will lower my ambition, and I will try to give some ideas on the exotic graph. Okay? The point is to understand, in fact, it can be done very quickly, actually. So we just draw a picture so that it's more clear, indeed. So a point that I didn't mention so far is the x of t, you see the equation of x of t. Xt is 1 over lambda square, so it's 1 over t minus t. Okay, so if I integrate, x of t is like 1 over t minus. So you think that the graph point is going to infinity on the right. Okay, so if I do a picture of the situation, we have the following. So my initial data is q plus some calculation, it's nice details here. I don't like too much what happens here. I just have an h1. This is initial data. So if I am in the graph situation, this will start compressing, and it will move to the right very quickly. Right? And when I'm close to T star, when I'm close to T star, the function is very focused. Okay? Its location is among 1 of T star minus t. Right? So it's going very fast to the right. And here it's the top and factor. I have the decay, and the decay is going to be scaled, so it's very small. And the residue of the mass is going to my chin. In fact, in the Kennedy equation, big objects travel very fast. Right? Whereas small objects cannot travel so fast. We don't have enough h1. So I have the coupling which is very important in the proof. And that is why we can show actually that epsilon goes to 0 very fast. From all this we can prove that this norm in fact goes to 0 like in real case time, that's 1 over t to the 7, something like that. So it goes to 0 very fast. Whereas the remaining part of epsilon does not go to 0 in L2, it's just the residue here. And then we work in finite time. But in finite time I have a residue, so we can call it a good sum. Okay? set. And this is going front to the right. Okay? So this is, I would say, the standard block, the block in A. So now, what is the strategy to get exotic block? So for the exotic block, what I will do is that I will do the same strategy, but on the background, on the back tail. So I put the tail, the explicit one, the power of X, which is N2, which is N1, sorry. I will put the solution on the top of it, and I will expect that the interaction between the solution and the tail will change the dynamics. In fact, I will complexify a little bit the equation, which is very simple. It's lambda t is constant, right? So far I have lambda t is 0. Okay, so that's very simple equation, right? So what we expect that if we put the tail, we will change this equation for another one, whereas the tail will have a strong influence. So this is what will happen. So the tail I'm talking about is the following. So I define f naught of x is a constant, which happens to be negative in our example. X minus theta, theta is to be chosen, but it will be chosen around 3 over 2. Technically, because a bit bigger or a bit smaller. So this function is indeed in H1, in H2, and this is only for x. Right? And you do whatever you like for on the left. Okay? What you said that this is a monster solution of the KDE equation. Because if you differentiate with respect to time, it's 0. That's not different time. This is not moving, right? It's a fixed state. So I put it here once more. So I put the tail like this. So it's negative, but and then I will put my solution on the top of it. Right? This is a monster solution because when I differentiate with respect to time, it's 0, as I said. When I differentiate with respect to x 3 times, of course it's much smaller because x is large. When I take power 5, of course it's much smaller. So all this is invisible. So I can do as is as not one solution. So I do the following. I consider a solution which is u of dx. I do the same way as before. I say it should be epsilon with k, and I add this. Right? This is a solution, right? This I expect to be a solution, but it's equal to the equation of epsilon, which is the same as before, except that in the nominal power, in the nominality, I will have interaction between f naught and this guy. And of course the bigger one, this is more because I have lambda x. So the bigger one will be the 2 to the 4 times the power 1 here. This is the biggest interaction I can imagine. Okay? This is the only interaction I have to take into account. So what we do, we write the equation for epsilon, and we do as before, and we add a term in the equation. But the simplest way to see it is to do the energy conservation. So what happens for the energy of this? So I told you before that the energy of QD, lambda, was G over lambda squared. So that's 2 constant, right? So I do the same, but now I have to consider that I have the energy of Q, it's QD itself, but QD is f naught. And in the energy, when I look at the gradient, it's a derivative, so it's a lower order. So what is the main term, as I said, is in the energy to 2 to the 5 times f naught. So in the energy, what I get is so constant G over lambda square, and then I get what is going to be important is the Q lambda 5 f naught. And this guy is moving, this guy is not moving. Since it is focusing, once I got a segment this value here is about 1 over xt of theta. Take the value at the point where Q is located, so the Q is focusing. So f naught is about constant. And this is for simple computation because that this is 1 over lambda square, but then I need the power to be 1 over lambda square. So I have lambda 1 half times then Q4, and then everything is divided by xt over this. Okay, so what I get is the difference relation, which is lambda t plus lambda minus 3 over 2 over x of t to 10. And this is constant. If I look for energy negative or zero energy, let's say, I will find that this is 0. So it's a different relation. And we happen to have a special solution. Remember that x prime is 1 over lambda square, so it's easy to take 1 lambda to make the derivative of lambda. Right? So we can very easily solve this equation. And we find solutions which are different from the one we had before, but find solution like this, for example. Okay, this is our solution. And I have the expression also for this x. And if you take theta to be 3 over 2, we find again t minus t. But if we take theta to be less than 3 over 2, we find a graph which is quicker than 1 over t. And if we take theta bigger than 3 over 2, we find a graph which is less than 1 over t. So in some sense, it's not anymore running our graph. It's a graph which is driven by a source. The source gives the date on which the solution is traveling when it's concentrating. Right? So the solution travels like this. And its dynamics is driven as a first order by the tail on which it is located. It's not anymore running our graph. It's something. So this is happening in H2 and H1. So it's a fact we have to face when we want to understand dynamic in H1. This is it. So I will continue. Thank you very much. We cannot do, if you take theta small, then we get growth in time, we get growth in infinite time. If you take 5 over 4 is a special here. Right, so in this proof we have this, some power here and then 5 over 4. If you take 5 over 4, you get something I don't remember, if you take something which is less than 5 over 4, you get growth in infinite time. And then if you take theta too small, it's not mentioned, so. And on the other side, take theta too big, of course at some point it does not the growth anymore. What we cannot do is to go with power that are too slow. So here we still have this restriction. So we don't even approach 1 over 3, which is just our constant. Yeah. Yes, but everything is done backward. We take a final data, close to block time, we take HF to the 0 at this final data, we make the evolution, everything is a set of estimates we have. So at a given time, if we have all light estimates, we have to present this time, and by week you position the flow, and we get solution with those this estimate for absolute. So it's a complex argument again. It is very similar to what we did for the minimum method. So, but because imagine we do the, for all guys in A, why not? With the same. This was not done, but why not? And it's not so interesting, but put it down. It's global, but this is the only thing we know. So we know it's global because we could put on one side the exponential decay. And we have another result for exponential decay in different data with minimum, so it's no problem. So the minimum is decaying on one side, exponential decaying. On the other side is similar to this. It's similar to some power. So it's very asymmetric solution. Which for this I think cannot be specified for the experiment. So because we don't know what happened for backward, so what we expect is scattered, but nobody knows how to prove it. It is in HFE. It's working, and we can also do some estimates close to the block time from that. But when we go back in time, it exists, the neighborhood of the solid, and then we have to stop the analysis. So it's a totally different story. We will need like a scattering theory of the sphere, of what is the water, and on the sphere for this we don't have it for the helix. Thank you very much for the introduction, and I owe a special thanks to William Diss and Demar Schindler, who I think have been extraordinarily courageous in organizing such a big meeting and helping to create this accident during such a, I think it's already a successful big meeting. There were no disasters, but there's been nothing resembling a disaster so far, at least, so I think this is a great success. It's certainly a great pleasure to be here in one of my favorite cities in the world, good topic. So when I heard that I would be speaking in a joint session, it helped convince me to be a little brave myself, so I'm talking on this topic which I've been thinking about. I was motivated by the archive papers, which appeared earlier this year by Bogan and Sullivan, and I'm just very much in progress in the sense that I don't know how far this will go, and there's so many ideas to explore. But at least it gives me an opportunity to explain how this is connected with recent progress on field battles and value theorem and this new method efficient complex things for investigating this. So first of all, I can tell you a bit about sort of background of motivation, which allows me to go backwards in time to things I used to think about more than 10 years ago. So let me define, and I'm calibrating my rhetoric. I will probably get smaller and smaller, so if you're at the back, you need to shout when it becomes unidentifiable. Okay, so let me define the number of solutions of a system of Dirac-Hunter equations. And these are equations, but not inequalities. So what I'm interested in for the moment is the number of solutions of a pair of equations, and I'll level like this. And I hope that I get efficiently used these later on. So I have one equation of degree k. K is an integer which is equal to 1. And for the moment, just to keep it simple, I will slice this with a corresponding linear equation. So here are my two Dirac-Hunter equations which I want to study. And then I'm counting solutions where all the variables are both b in size, so b is some large positive number. And so this is a counting problem. I'm counting integer solutions of these equations. This exercise x and y are integers, and this integer k is 2. So this is it. And this is a very classical problem. It's been out there many times. So really a classical result. And I'm not sure who was the first to investigate this. I mean, in some sense, the situation where k equals 2 probably been a 19th century result. Sonny Koala investigated this in the 1940s. So it's known that when k equals 2, the number of solutions is asymptotic to a constant times d cubed log d, the large value speed, and the constant is even 15 over pi squared. And for the very precise asymptotic formulas available these days, thanks to Buddha and Robert, or Robert Buddha, so let's just take this 2010 over the asymptotic formula with low order terms available. That's what it does it. Okay, so when you're dealing with problems involving such as squares, the classical machinery is available and money to do quite well without problems involving squares. So then, if you're interested in how about that? Good. If you're interested in degrees larger than 2, then life gets a bit more interesting, a bit more difficult. So the first result that I know of in this direction is 2 sub 1. I suspect I had this before 1947, but it certainly appears already by 1947. So if you're interested in corresponding problem involving cubes, then it's possible to obtain an estimate which is to go into a perceptual, very positive number estimate. And in fact, what proved was a result of this type where there's even an explicit power of log e here. This is log e to the 9, if I remember correctly. And this is a result which has been rediscovered many times. So certainly, Bogan and G. Brown made use of this result in the 1980s. And this is a result which has been refined. So, for a number of object solutions to the system of equations. So if I take the x's to the permutation of the y's, then you can get a solution which has order of growth 50 cubed. And then you can measure how many solutions there are other than these obvious diagonal solutions. So these are the ones where x1, x2, x3 is very small, so nobody can see the map, is the permutation of y1, y2, y3. And then the other solutions contribute something which has order of growth b squared or b squared 5. That's something that's Gordon and myself proved in 1995, well, I think I published it in 1995. Well, spectacularly, believe it or not, I formula for this secondary term, which is improved more recently by Philip Research. The audience who could tell me when it was published, but it's 2007. It's no. Okay, good. So carrying myself a little. So you see, this is something which I try to describe as a positive result, because the obvious diagonal solutions and then the number of non-diagonal solutions and all the numbers is definitely much smaller. So almost all of the solutions of this equation when k equals to be a diagonal, which is definitely not the case for the case k equals 2. That's a general phenomenon. So if you look at the such a case,